So the root test in the textbook gets packed in with the ratio test. They're the same section. And the ratio test is the really important one, and the root test is less important, but it's something we should know. The root test looks a lot like the ratio test. That's why they're taught together. You take a limit and you look, and if the limit's less than 1, it converges, and if it's greater than 1, it diverges, and if it's equal to 1, it's inconclusive. So the exact same sort of structure as the ratio test, and it's the limit as n goes to infinity of the nth root of the absolute value of a sub n. And I said it verbally, but let me get it in writing. Less than 1, convergence. Greater than 1, divergence. Equals 1. The test is inconclusive. We don't know. And it might seem at first blush that this is actually nicer than the ratio test because you don't have any big fractions. The fundamental issue here, and the thing that makes this test so specialized, is that we do not, in general, know how to take the limit as n goes to infinity of the nth root of something. So, I mean, if we have this, for example, we could approach in a very nice way with the limit comparison test. If we tried to use the root test, we get this, and the sort of the problem here is that the thing under the root, well, is going to 0, but the nth root of a fraction, the nth root of something that's less than 1 is greater than the fraction. So this nth root is driving everything towards 1, and 1 is a failure state. If the limit is 1, then we can't use this test. And it's really unclear. I mean, when we have a fraction from using the ratio test, we have ways of dealing with fractions. We have L'Hopital's rule specifically. If n is big enough, everything's positive, but I guess I did forget the absolute value. This is really difficult, and we've never done calculus with something that looks like this, where our variable is simultaneously in the base and in the power. So the root test gets sort of relegated to specific situations where we have a power that we want to get rid of. Something like that. If we just look at this, we might be able to get clever and use the comparison test, but none of our other tests seem very hopeful here. If we try to use the ratio test, we're going to have terms that look like this, and we won't be able to do any of the simplification that we want when we use that test. This doesn't really look like anything as far as the limit comparison test. Nothing's crying out to me. We don't know how to integrate this, so we can't use the integral test. The nth term test is inconclusive. But because we just have a power that we want to get rid of, the root test comes through. And everything's positive here, so I didn't forget the absolute values. A root of a fraction is the fraction of the root. So we can do this. It doesn't matter what n is, the nth root of 1 is 1. And it doesn't matter what n is down here, the nth root and the nth power will cancel each other out. If you prefer to think of this another way, the nth root is the 1 over n power. When we have repeated powers, we multiply them. So this becomes 1 over n. And then when we take the limit as n goes to infinity of this term, it's the limit as n goes to infinity of 1 over n, which is 0. And 0 is less than 1, so the root test functions, and it gives us convergence. This series converges. And this example is very typical of how the root test gets used. We have a power, the power is causing us problems. Other than the power, things aren't super complicated. Another example would be if we had something like this. Once again, it's really the power that's causing us trouble here. I mean, if it weren't for the power, we could use, the limit comparison test, probably. Or really, if it weren't for the power, we could use the nth term test. We could say that this is not approaching 0. But because of the power, we can't. The power causes this to approach 0. So what's going on? Well, the thing that the root test is really, really good at is getting rid of powers you don't want. The nth root and the nth power will wipe each other out. We actually think that we do need the absolute values here, but the nth root and the nth power, as I say, wipe each other out, and we get the absolute value of this expression. And you ask what happens as n goes to infinity. Again, just like the ratio test, we're taking a limit here. Well, depending on how comfortable we are, we can either hit this with L'Hopital's rule a few times, or we can say, well, this is a rational function and it has a horizontal asymptote. And because these degrees are the same, the horizontal asymptote is gotten by dividing the leading coefficients. 3/7 is less than 1. This converges again. And notice, I mean, we do need the absolute value here because this is getting negative as n gets big, and eventually, like the 40th root and the 42nd, I mean, these are going to stop being defined without that absolute value. So it is serving a purpose. It's also, you know, if we had 5n, let's just take this and tweak it a little. Let's put the 7 up here and the 3 down here. If we didn't have the absolute value, we take the nth root of this whole thing, feeling a little lazy, I guess. The nth root and that nth power cancel each other out. This converges to -7/3. -7/3 is certainly less than 1, but this series does not converge. We've made a mistake. We've left out the absolute values. When you put the absolute values there, this is +7/3. It's greater than 1. So those absolute values are pretty important. And let's do another example. Just something a little messier. So this n to the n, that's screaming out for the root test. So 1 plus 2n there. So as I say, I mean, the root test is a little specialized, but it absolutely has use cases. And this is absolutely one of them. When you see an nth power, you almost have to try it at least. So everything is positive here. I mean, the absolute values, we can put them in, but they're not going to do anything. So we've got the root. We've written it as a power because that's going to make the algebra more straightforward, I think. So when you have a fraction raised to a power, you can take the top to the power and the bottom to the power. And the top to the power, we multiply the powers, n times 1 over n is 1. We get n. Down here, there's not that immediate simplification. We multiply the powers. But what is this? Well, we can do the algebra. We can multiply through. So this distributes. So 1 times 1 over n is 1 over n. 2n times 1 over n is 2. And we didn't have, the total cancellation we got in our earlier 2 examples, but this is good enough. Remember that we're taking a limit of this. And as n goes to infinity, well, n is showing up twice here, but let's just take this piece by piece. As n goes to infinity, this goes to infinity. 1 over n is going to 0. 3 to the power of 0 equals 1. And this is infinite. And again, keeping our test straight in our mind, with the limit comparison test, infinity would be a failure. With the ratio test and the root test, we just think, well, infinity is greater than 1. And we sort of treat it as a number in that respect, which we always say not to do. But this whole thing diverges. What I might do, we have 30 minutes left. We need to cover the alternating series test. I might cover the alternating series test today and then not meet tomorrow. Just because I think ending today with 30 minutes left and then having a lesson tomorrow that's under 30 minutes is not respectful to anybody's time. Because the alternating series test is going to take, 10 minutes to present, maybe. We do need to start with a definition. An alternating series is a series where, where the terms alternate in sign, in positivity or negativity. So here is an example of an alternating series. You see, we go from positive to negative and negative to positive. Every term is a different sign than the one before it. And the alternating series test is a little like the nth term test, but the opposite of the nth term test. The alternating series test can show convergence, but not divergence. Suppose 1, these terms are going to 0. If they're not going to 0, then the nth term test tells us that this does not converge and there's nothing else to do. 2, these are going to 0 monotonically. This is a condition we've seen before when we had the integral test, but suppose that every term in the series is less than the one before it, then the series converges. So it's frequently quite easy to decide whether alternating series converge or not. The alternating harmonic series. This is the harmonic series, except that every other term is negative, which, incidentally, if you were writing this in sigma notation, you make a series alternate by having a -1 raised to a power. Well, when you're using the alternating series test, you're ignoring the signs. You're looking at the rest of the series. And certainly 1/n goes to 0. And 1 is bigger than 1/2, which is bigger than 1/3, which is bigger than 1/4, and so on. These terms are going to 0 monotonically. So this whole thing converges. diverges. This alternating series does via the alternating series test. And you can make it a little, how do we know? I mean, as far as taking the limit as n goes to infinity, that's L'Hopital's rule most of the time. How do we know that these terms are getting smaller? I mean, you can get in the weeds if you want to. If you wanted to demonstrate this in a super formal way, you could say, well, the derivative of 1 over n is negative 1 over n squared. This is always less than 0. It's always less than 0 because n squared is always positive, and 1 is always positive. So this fraction is always positive, and you put a negative sign in front of it, and it's always negative. And then you say, well, a function whose derivative is always 0 is decreasing. To me, this is getting a little in the weeds. It's like if you're actually like publishing an applied mathematics paper, you might spend a few lines showing this, you might not. You might just say, we can use the tools of calculus to see blah, blah, blah. But I mean, in most situations where you're using the alternating series test, it's obvious that the terms are getting monotonically smaller, and worrying about, but can we show that the derivative is negative? Again, it feels like it's getting a little in the weeds. Also getting slightly in the weeds, but it's something we, of course, should recognize, and it's something that I said out loud. The alternating series test can only show convergence. It can't show divergence. Can I find... Oh, well, I said that a little wrong. I mean, it's true. If the alternating series test fails, we don't get any information. The series could diverge, the series could converge. There's no way to tell. It's very easy to find a situation where the conditions of the alternating series test are not met and the alternating series diverges. In fact, we've given one. Brandy's series is an alternating series. It does not satisfy either of the conditions of the alternating series test, and it diverges. As an example, where the conditions aren't met, but the series converges anyway. Here we start to get a little artificial, but let's look at this. -1 to the n minus 1 of 1 over n squared. So this is not the example we need. Here the conditions are met. 1 over n squared is going to 0, and 1 is greater than 1/4, which is greater than 1/9, which is greater than 1/16, and so on. An alternating series that converges using the alternating series test. As a matter of fact, this series converges absolutely. If you put absolute values around it, we get a p-series, and the p-series converges. So this series converges absolutely, and we haven't done anything with absolute convergence. But one thing I have said is that if a series converges absolutely, we can treat it like a finite sum, and we can move stuff around. So we can swap those two terms, and it doesn't change anything. And we can swap these two terms, and it doesn't change anything. And we can swap these two terms, and it doesn't change anything. And what we've constructed, rather artificially, it has to be said, but we've constructed a series that converges, but does not satisfy the terms of the alternating series test, because 1 is bigger than 1/4, and 1/9 is bigger than 1/16, and 1/25 is bigger than 1/36. It does not satisfy the second condition. It is not monotonic, but it does converge. So if the alternating series test fails, we have to try something else. And concretely, if it fails, we have to try either the ratio or the root test, because those are the only tests we have that work with negative terms. All right, even if, let me not record what